Yo, Gabi, you hear me? Yeah, I think the volume is way too loud. Let me see. Let me adjust that. Okay, it's a little bit lower now. If it's too loud, you please warn me. Yeah, it's because my fan is on. Let me just. Okay, better now? Yeah, the noise was because my fan was on, because it's hot as hell here. So I just turned the fan on. But now I turn it off and it should be better. Okay, so you guys let me know if it's too bad, the sound. It's good now, okay. So what's the idea today? So we got the board laid out, right? So we got the footprints here. The board has got 50 keys. So if you look at the schematic, that's the schematic, right? So we have got 12 columns and 4 rows, okay? So imagine just these guys here. There are 3 switches here, which are the 2U switches. I'm going to I'm going to explain what they are. But just imagine that we have a key matrix of 4 by 12 keys, right? So that's the basic board. Who are these guys here? So these guys here are the mounting holes, as the name suggests, right? So there are these guys here, this guy, this guy, this guy, this guy, right? We've got the microprocessor, which is in an 80 mega 32U4. That's the guy here, and the other components, right? So this is the USB connector. These here are 4 capacitors made to regulate voltage, VCC voltage. This is the crystal, frequency crystal, and this guy here is the reset switch, right? So what's the idea here is that in the RST pin, which is in the microprocessor, I think the 34th. Let me check that. Who's that? No, the 13th. So the 13th is the reset pin. What this means that this means that if this reset pin is made 5 volts VCC, the microprocessor ends reboot mode, so it loads the flash again. That's what generally you do when the board stops responding or it shows some odd behavior, which is not common for a simple board like this, but it's good practice to put it, because in the next editions we are going to insert like RGB lighting and LED and these kinds of things, so the board gets sophisticated, and it's nice to have a hardware mechanism so that we can reset the board once it's shown some odd behavior. So that's the general idea. That's the general idea of a keyboard board, PCB, right? That's the basic schematic. From this board to what's gonna change? Well, we're gonna add a LED matrix, an LED matrix, right? So it comes next. And that's basically it. For a board that supports in-switch LEDs, if you'd make a bigger board, what would you use the same number of components? The components that regulate voltage. Yeah, I mean, these guys here, they are here just for security, because the VCC voltage in computers, they're usually well regulated. So you need this. Why do you need this? This is basically to regulate locally. What do I mean by locally? So if you take a look here, this is a microprocessor, right? Which is this guy here. Okay, so this is the microprocessor, right? So you see that the board is full of copper, right? So it's covered in copper, and the voltage comes here, right? So what happens is that when the current, electric current from the computer here, it travels a little, right, with copper and stuff. In this way, in this current path it takes, it can get some noise, it can get some discharge, it can get some, well, actually anything that can make the VCC float. So what do we do? We put these four guys here so that they regulate the voltage locally. See, so in the VCC that comes to the microprocessor is quite on point. Hey Wix, how are you? We are discussing the PCB SharkPCB project, right? So just so you know, I have this. So the people that I just seen that Gibbs finished his stream, and he brought some people up. So hey people, how are you? So what's the idea here that I'm showing you is the SharkPCB, right? So I have this open source project, which is an Ortho 40% project. Anyone can access it, right? So if you come here to my GitHub page, which is github.com/gondolindrim/sharkpcb, you're gonna see the whole project. Hey Keeps, thank you for the stream highlight. Thank you much, man. Much love. So anyone can access this. Anyone can contribute. Anyone can produce this, and we are producing it so anyone can take a look and see how a board is made. And my idea here is to make sporadic, seldomly live, so that I can explain how do I design my boards and which are good practices of board design, and how a keyboard works under the hood, right? So how it works in the fine details. Is it ALPS and MX? No. At its current state, it's MX only, right? So if you look at the at how it is right now on GitHub, it is MX compatible. It is ALPS compatible. So I quite don't like that. Gonna go have dinner. Okay, hey, please come back, man. Would be good to have you here. So as it is right now on GitHub, the master repo, it's MX compat because I took the footprint from Rui Kimau, I guess. The footprints here, which are MX only, are my own, and they are on the second branch. There's a second branch called MX only, which is going to be this guy here. So if you want an ALPS compat board, you can have that. That's there. If you want an MX only board, I'm designing it right now. Okay, so that's how I'm doing it. The good part here is that I'm designing this board from the ground up. See, so the only thing I have right now is the board outline, which is this yellow outline here, and the components placed, right? So I have the switches placed, and I have the diodes placed. So there are no copper traces here. What's wrong with ALPS compat? So the problem with ALPS compat is basically two problems. The first is that not many people use ALPS. Second, the switch holes for the ALPS compat, they're way too big in my opinion, and you just butcher all much more than was needed of your board. So if you take a look here, let me get back to the GitHub page. github.com.go. So if you take a really close look here in the GitHub preview page, you can see that these switches here, for example, under here, they are way too big, right? And that they get cut down by the stab cutouts, and I don't really like that. The second problem, another problem, is how you were going to find a keycaps for an Ortho ALPS board. Yeah, that's exactly the problem, right? So I'm going to leave it there. I'm going to leave the ALPS board there for anyone that wants to use it. And it's open source. Anyone can use and produce it. But the thing is, I want an MX only board, because my idea in the future is to make this board a fully operational one, like with LEDs, with RGB LEDs, As you guys can see, this here is compatible with Planck, with Planck cases. So any case, I think the High Pro case and the Mid Pro case, this board will fit right in those cases, including the screw holes. So it's a ready to use board. It wasn't prototype yet, so I can't guarantee 100% that it will work. But I have this guy, Steve of Wood Cables, who is prototyping it, and it looks pretty good. It looks like it would work. So what are we going to do today? So the thing is, I wanted to get questions from you guys of the general project, of the general design of keyboards and electronics in general. So ask me anything. AMA, right? And I want to take questions of you guys on how I design my personal boards, because we have the SharkPCB, which is a 60% hot swappable board coming. We have the Arctic PCB, which is a multi-layout 60%, right? And I want to be transparent to you guys on how I design my boards and how do I do it, and answer your questions on what to do better, what's better for the long living health of your keyboard. So that's what we are going to do today. Notice that, so as I was saying, we have here, what's a keyboard basically? It's just a matrix of switches, right? So what's happening here is that if you press switch 1, let's say this switch here, you have the column 1 and the row 1 will be short-circuited. In the microprocessor, this means that pins, let me see how it is configured here. So column 1, row 1, column 1 pin 32 and row 1 pin 22, they will be short-circuited. So that's how the microprocessor, basically, how the microprocessor knows what key was pressed at the exact time. So a keyboard is basically a matrix of switches. That's basically it, and it detects which switch was pressed based on which row and column are short-circuited. The thing is, the main problem here is to adjust multi-layout. So as you guys can see, this board here, it can support full ortho, meaning 4x12 1U keys. It can support a 2U spacebar in the middle, and it supports two 2U spacebars here. So how do we do that? Well, that's simple. See that I have here 3 more switches. So which are these? Switch 41, 42, and 43 are 1U switches. They are these guys here, 41, 42, and 43. And then switch 49, 50, and 51 are 2U switches that are put exactly on those guys, and they are wired so that they substitute 49 substitutes 41. And why can I just short circuit this? Because if I'm using 49, I won't use 41. See, because if I use 49, 41 is unusable. If I use 50, 42 is unusable. And if I use 51, 43 is unusable. So I can just short circuit them. So what I have right now is this board. The components are placed, but I have no traces on them, and I'll have to deal with these guys here. So what's the big problem with PCB design? It's the tracing part. Okay. The big problem here is tracing. The component placing, in like 90% of the cases, it will be mechanically determined. What do I mean by that? I can't just place switches any way I want to. Let's say if I place this switch a little bit to the left, it won't fit on the case, right? Chances are that the key switches will collide. So the measurements and the component placing, they are generally predetermined mechanically. So component placing is not very difficult at times. What's really difficult in PCB design is 90% of the cases, the tracing. So that's what we are going to do today. We are going to trace the copper vias. Do you guys have any more questions on how, on what we are going to do today and the explanation I just gave? And I forgot to mention that these footprints here that I used, they are also open source, and you can also use them on our personal projects. They are not commercially available. If you are going to use them commercially, there's no problem in using them. Just give me an issue on GitHub, and I will license you. It's used. I just mainly want to know who's using it. Okay, so you guys got it. So what's the big problem here? The big problem here is placing the SMD components, right? Because if you take a closer look at the 3D model here, the SMD components, they have to be placed in such a way that they won't disturb the other components. What I mean by disturb, you see, that's the microprocessor. You see that it is almost touching this switch contact here. It is almost there. So what's the problem here? The problem here, this register, by the way, it's just misplaced. Let me put this on another place so that it won't be misplaced. There you go. What's the problem here is that there is a limit to the distance between two pads that I can put, right? So let's say if I get a major PCB producer, say GLC. So when you go to GLC site, you can go to this tab here called Capabilities, and it will give you a bunch of constraints on how you can design your PCB, right? So if you take here item layer, you can have up to 6 layers. In this case, we have a 2-layer PCB, right? We have the front and the back. What would be a 4-layer PCB? There would be 2 layers inside the PCB here. See, so there is the FR4. There would be 2 more layers inside here, in the middle here, inside the board, and it's convenient for like intricate projects and sophisticated projects, but I think for keyboard and simple PCBs like this, it wouldn't be needed. What website it is? This is JLC, right? So you go to jlcpcb.com. It's a major PCB producer in China. You can produce almost any PCB you want here. In fact, Arctic PCB, the Rev 1 of Arctic, and Keeps PCB were produced here. They are already in Brazil, yay, and they are coming here so that I can prototype them. Big props to Keeps. Keeps actually funded it. Keeps actually paid for the whole thing, so props to him for that. Thank you so much, man. And I can show you guys how to quote it. I mean, once I have this done, I can quote some and produce some so you guys can see how the whole process is done. But what I'm interested in right now is the capabilities, right? So what are main constraints when I am designing my PCB? There are many here, you see, so I have up to 6 layers. I have only FR4 materials, so there are many materials that can be used for PCB manufacturing. The best one of them is FR4, which is glass fiber, I guess. The maximum dimension of your PCB, so 40 by 50 centimeters. The Imperial system guys, they cringe when they say millimeters. The tolerance on the dimensions, right? So let's say you have a 10 centimeters by 10 board. So it's gonna have 10 by 10 plus or less 0.2 millimeters. Solder mask. The solder mask is it's like how do they there's a nice video how they produce their PCBs, but the solder mask is it's a mask they produce to the the light-based, laser-based system they use a system based on ultraviolet incident bright light, and it's quite nice. Board thickness, right? So the default thickness of boards is 1.6 millimeter, I guess. But if you want another other thickness value, they can produce it. They have thickness tolerance. The main part here are basically this one, minimal trace. So the copper traces, they must have 3.5 mil or more. A mil is 1/1000 of an inch, right? Between two layers, I have a minimum of 3.5 mil. For double layer or single layer, the minimum is 5 mil. The drill size, minimum via hole size, is 0.2 millimeters. So these constraints here give me the maximum and minimum values I can put in my design rules when I'm designing my PCB, right? How do you do that in KiCad? So the basic thing you have to do, every PCB project starts with the design rules. So let's say let's say I have a copper trace here, right? So if I want to trace another copper trace here, say this guy here, okay, so there's a second copper trace here. Their distance is something along the lines of here, something like 0.06 inches, 0.06 to 5.06 inches. You have to ask yourself, yeah, but can JLC produce my PCB when two traces are 0.06 inches apart? The answer is yes, they can. So you have these rules that you have to attain to once you start designing your PCBs. All the single layers, all the single layers, all the single layers. Dang, that's catchy. Yeah, all the single layers, man. So that's it. So how do you do that? You see, you can configure that on KiCad. So if you go here, preferences, let's see, general settings, I guess. No, that's not it. Tools, manage footprints, display options, files. Where is it? Setup here. Setup design rules. So it's gonna pop up this big window, and there we go. Default clearance. So what's the clearance? It's the clearance between two layers, right? So we go on the JLC side. We see that the minimum clearance here is 5 mil. So I go here and I set this up, 5 mil. There we go, 5 mil. Track width. So what's the minimum track width that I have to use? I have to use, let's see, where's the JLC side? Track width, 3.5 mil. For single and double layer though, it is 5 mil. So there I go, 5 mil. 0.005. Via diameter. So what's the minimum via diameter? And I keep configuring it. Let's say via diameter, 0.05 millimeters. So there we go. The problem here is with the GLC capabilities is that they mix up. They have some units in mil, which is inches, right, imperial system, and they have some in millimeters. So I have to convert them. So what's half a millimeter in mils? So there we go, 0.5 millimeter in mils. So it's something like 20 mils. So there I go, minimum via diameter, 20 mils, right? So 0.2. Minimum via drill, so 0.2 millimeters. Yeah, now we have to see how that goes. 0.2 is something like 8 mils, right? So always round things up, right? 0.8 mils. There we go. This micro via stuff, you don't have it. Differential pair and differential pair, I just don't want to explain it right now, but they are another project constraints, and they must have that there. Let's see. Do they have this? Micro vias, yeah, they do, and yeah, so it's configured for what it's worth, our project is configured here. So when we get back to our PCB thingy, when you are round P to 4, yeah man, P is 4, that's it. When we are placing the copper via, you see that KiCad puts this gray outline on it. See this gray outline? It's the 5 mil that the minimum 5 mil allowed. So once you have that configured, it becomes much more easy to do the stuff you want, right? So there it is. Having all those minimum and maximum values configured, then it's time to trace the PCBs, the PCB vias. The only thing prior to that is always have in mind that PCB tracing has two main problems. The first is clearance. I mean, three main problems. The first is clearance, so the clearance between two vias. The second biggest problem is the minimum width of the via, and the third problem is the maximum width of the problem. So what do I mean by maximum width? So if we go here, let's see, there's this nice site, PCB via with calculator. So what's the problem? So the thing is, if you take for example the AWG table. So what's AWG table? When you are designing when you are designing the wires for your house, for example, you have the current that passes through each wire, right? So when you go there, like the AWG 11 has 2.3 diameters in millimeters, it can take up to 12 amps. The 12 wire, it can take to 9.3, and there you go. So what's the big problem here? The same thing goes for PCB traces. What do I mean by that? This trace here, which now has, what's the width? Something along the lines of 10 mils, right? So there we go, 10 mils. This width here can take up to, this calculator tells us, external, no, 0.1, something along the lines of 0.2, 0.3, 0.1 amps. So every width, every copper trace has its maximum amperage, its maximum current it can take. What's the big problem in there? The big problem is that this is the USB connector, right? So the current comes from the computer through the USB connector in this pads here. If you count all the LEDs and the microprocessor, your board needs something along the lines of, I guess it was 400 milliamps. So if you take here 0.4 milliamps, you need at least 1.67 mil here, right? So you always have to have in mind how much current goes through that via, that particular via you are tracing, and that it has this minimum width due to that amperage. So I said a lot, but did you guys understand? So when I'm tracing a via, I have to always have in mind that this via conducts some current, and because of that current, it has a minimum width I have to make it. Was it clear? And how do I calculate the minimum via? Well, the calculations are kind of complex, are kind of big, but there are many websites that make it easier for us. So what does this website tell us? So if you have a minimum current of, let's say, half an amp, for external layers, you have to, the particular trace you are tracing has to have at least 2.3 mils so that it can conduct 0.5 amps. This is considering that the temperature rise of the trace is 10 degrees Celsius and the ambient temperature is 25. If you change any of those parameters, the overall results change. So if you don't want the trace, the via trace to rise 10 degrees Celsius, you want it to rise, say, 8 degrees Celsius, there you go. It rises in 9 mils to 10 mils. So you always have this constraint on the tracing width. So say, for example, I want to conduct 0.1 amps, 1 degree Celsius. I have to have at least almost a mil. So what's the big thing here? The big thing, all this that I said wraps up to you have to know specifically how much current each via is designed to conduct. So everywhere, at every via, every connection, you have to have in your mind that that particular via has a minimum width. You got me? So this problem it's more apparent when we are talking about LEDs, right? So for example, this trace here, which is a trace that comes from the switch to the diode and then to the microprocessor, it conducts no more than a milliamp, 1 milliamp. So it can be quite thin actually. The big problem here is this one. So we have a VCC here, right? This pin VCC, it conducts, I think, up to half an amp in mini B connectors. So you have a minimum trace you have here. Okay guys, so I'm gonna start now tracing this, and in the beginning it's quite easy because you see in this part of the board here you have a really clean and clear path. So these guys here, I have done 2 of them. You just have to, there you go, trace one. Trace this. Now what's the width here? 10 mils. How do I make the default? Let's see, rule, setup design rules. So what's the default via? Minimum via. Where do I set the default via width? Setup layers, text default, pad properties. I don't know. Well, so there you go, via. Okay, so we keep on tracing these guys. Okay, so this guy is wrong. Let's check it. So guys, you can take any questions you want and just make them. I'm here to answer your questions. I'm like the electronics genie or something. So this guy is done. Okay, so this guy's done. I'm gonna close the 3D preview so that it won't. I'm gonna close this to make it faster. What can I close here? I can close this. No, we can't. Okay, so this guy's here. So what traces am I tracing, right? So for example, it's really nice in KiCad because you can take a really nice look on what you are doing. So what's this trace here? This trace here is this guy here, you know, so SW8 here. So the trace I just did was this little green here from the switch to its diode. And these are the traces I'm doing right now. So I think they are getting too thin. Let's see. Edit all tracks and vias. Ah, there we go. defaults. Place setup, design. Where are the defaults? Track with. No, let's see. Design rules. Minimum track width 0.05. Minimum via diameter 0.02. Minimum via trail 0.08. There we go, and we change the defaults to clearance. Let's say 0.1, and this guy, let's say 0.1. Okay, so it's done. There we go. So so now I'm doing this. I have to redo these ones because they got too thin. Oh dang it, I'm just gonna global delete them. Tracks, okay, yep, done. So let's redo those. Here we are. Okay, so this is done. This is done. Yep, click, there we go. So the nice thing about this is that it goes right to the preview, right? So you can see it here. Let me just update that. Okay, so it recalculates, and there we go. So if you take a nice look here, there it is. The two layers, the two vias that I just placed, there they are. So if I take a nice look here, there you go. So here they are. So what's nice about this 3D viewer is that I can see in 3D what I'm doing, in the sense that you can check how the tracers are placed, and for example, you can see that while this guy here, you can't place anything in the front side here, you can place something in the back side, you know, here. So there's no one here SMD. So the 3D view is nice in that sense. You can place the things and see how they are going, basically, to be put on the board. So I'm just going to take those. Let's see. Eventually, my biggest problem will actually be. Yeah, I want to trace this. Why are you not? Dang. Eventually, my biggest problem will be in this area, right? So while I'm tracing these guys here, which are quite actually easy, my biggest problem will be here, right? So we'll have many traces coming out of and in this processor. We'll have many traces coming from these guys here, which are the regulating capacitors. This guy here, which is the crystal. So the problem in keyboards in general, it comes down to this area here. 40% is actually a really difficult layout to trace because it's everything is just so condensed, right? So everything is really close, and you have to place and trace things so that they just don't collide. It's really difficult, actually. Okay, so here we have the first row done. Oops, I clicked the wrong thing. Here we have the first row almost done. pardon. Okay, so this is a problem. See, what the big problem here in this area is this. So if I route this guy here like this, so let's say routed it like this, you see that I'm just blocking the traces that are coming out of the USB connector, right? So this connector here, it can replace something along, let's just change the grid a little bit. 3, 1, 2, 5, 5 here. It can be placed somewhere around here. So you see that I'm gonna block. There are some traces that are going out here in this way, right? Out of those pins. So I'm gonna block them. So I'm actually not going to place this trace here. What I'm going to do is first change this so I don't lose my grid. So 6 to 5, 6 to 5. And I'm going to place this in the back copper. Back copper. Okay, okay, okay. So when I'm tracing these guys here, when I'm going to trace this guy here, I can do something like this, right? So I can do this. Yeah, I want to trace this. Why can't I? So here you go. So I can just, you know, do stuff like this. So yeah, I think I have to take another grid settings. Let's say 0.01, 0.01. So when I do this, I can do just like this, right? So this guy here, this is GND, right? So it can just be short-circuited. So I short this. There we go. So yeah, see that if I had this this trace here in the front copper, I wouldn't be able to do this. So you see that there's a recurring, and it's really recurring, it happens all the time, that I have to place some traces in the back copper so that I free up space for other traces. The big problem rises mainly from the SMD problem, which is the SMD parts, they can access only one side of the PCB, right? So if you take a close look, let's say these guys here. So these guys here, they cannot access the back copper, right? Because they are not through-hole pads. They are only SMD. They are only traveling in this front copper. If I want, say for example, this guy here to access the back copper, the second layer, the back layer, what I need to do is place a special, let's say, through-hole pad for it. So I do something like this, right? So it's a through-hole copper. I get this net name. I do this net. Oops, not this one. This one. So R3 pad 1. So there we go. Net R3. Where is it? R3 pad 1, and then I can do this. Okay, so now this guy, this pad here, it has access to the back copper. If I go to the 3D model, right? So there we go. See now that my resistor here, this pad here, this is SMD, and then it cannot access the back copper. Now it can, because it has a little THT connector, THT pad here. If you look at the back copper, there we go. See? So now from this little hole here, I can access this pad here. It can access, see, anywhere in the back copper. So the SMD has this disadvantage that while it's a little bit more reliable and it's lighter, smaller, it can only access one part of the PCB. So it's always going to be a trade-off between THT parts and the SMD parts. I always have to manage which layers are going to be mostly SMD stuff and which layers are going to be mostly SMD parts. In this case here, since this PCB is fairly simple, it doesn't have LEDs yet, LEDs yet, what I'm going to do is, and this is a good design philosophy, I'm going to make it as, I'm going to add as much traces in the front layer, in the red layer, as possible. I'm gonna try to avoid tracing vias in the back copper. Why? Because when I put the LEDs here, I use the back copper for that, for the LEDs, because all the LEDs will share a common net, which is the LED MOSFET, right? So the LED are controlled by a MOS switch, which is in itself controlled by a PWM this PWM, the microcontroller that outputs this PWM so that you can control the dimming in the LEDs. So all the LEDs will share this PWM signal. So when I add the LEDs, I'll just keep this back copper layer for that particular tracing, for that particular signal. So you guys, did you guys get the problem? My problem here, the SMD thing versus the THD thing. The problem, which is placing vias in the back or the front copper. This is a recurrent problem, right? This happens all the goddamn time. So let me just rearrange a bit here. 625, 625. So right here. So I'll just continue to do this. Okay. Okay, so when we reach the limits of the PCB, right? So either the bottom part or the right part here, you see that I don't have any more space to put my my diode. So what I did is I put my diode here in the bottom of the switch. That's why I have this these 4 diodes here, because this guy, it has 2 problems. I can't put its diode, this switch, the 48 here. I can't put it under, neither can I put it in the right place, this right side. So I have to put this guy here, and the 36 I put here. So this part here, the bottom right part, they are quite problematic when you are placing the diodes and the LED resistors. So I have finished having finished yep. Here we go. Here we go, and you go there. Yep, there we go. So we have the first row entirely coppered. Now I'm going to do this, right? So this is the first column. You see column 1. So what I did was this. So this is the first row, right? So here it says row 1. I'm going to just short all of them. Here it is. Okay, I'm going to short it right here. Okay, now now a problem has come. So I have to make a trace from this guy here to this guy here, right? There's this this line, white line here. So if I did this here, say this would be a problem for me in the future. Why? Because as you see, I have the LED cutouts here. So when I place the LED, let me just try to do that now. Let me change the grid first. Grid settings. When I try to do this, I have to change it one more time. 05, 05. Okay, now it's nice. When I do this, when I get the THT LED, when I put the LED here, see that it's the trace, the copper trace that I just did. it was not nice. You see, it was just too near. It was just too near the pads. So actually, what I'm going to do is I'm going to redo this. There we go, and I'm going to do something along the lines of this, right? So see here, here, and here. So there we go. So it's done. It's done so that when I place the LED here, it won't be way too near the LED, right? So I have to change the grid. Guys, I keep changing the grid because you have to always maintain one grid that you are working on. What do I mean by that? So when you are placing the switches, the distance between two switches is 3/4 of an inch, right? Is the 1U. So I have to place them 3/4 of an inch apart. So you see that I adopted a default distance there, which is 0.75 inches. And and I'm gonna base my work on that grid size. So every every copper trace that I place will be done in this grid here, which is better for me because I always keep on the same tracks and the same grid for every trace. So sometimes I have to change the grid because the actual grid is way too coarse or way too fine. So I keep changing them, but I always keep coming back to the same default grid that I set first. You see that the problem that I described with the LEDs and this distance here, it also comes back in the traces that I just did here, right? So this trace here is too near, this trace here is too near. So always try to trace these vias the farthest you can from the LEDs here. So I'm going to delete all of that. Let's see. Yep. So I'm just going to do this. So this trace here. So there we go. No, one more. And there. Done. See, so now I just have to do this. You are done. You are done. You are done. You are done. You. Oops. You. And this. And you. Yeah, now see the first row here, it's almost complete. Now I have just wired this guy here. Done. And you are done. There we go. So yeah, the first row here, it's done. See, when I go to the preview here, I think I have to update the preview. Close. It's frying my computer. Why the crap won't it show? It won't show on the 3D viewer, and why would that be? That it won't show. I have no idea why it's not showing on the 3D viewer, but you guys got the feel of it. So that's the general problems that come to tracing the PCB. So I have to close the stream right now, but what am I going to do next? So next Tuesday I will do this part here, right? So what I want to show you guys is the, don't you need regen the mask? I have no idea, I did, right? So yeah, I have to regen the polygon. So wait a little. It doesn't update the polygons right away. I'll teach you guys about the polygons also later. Yes, so there we go. Thank you, Blind. So yeah, there we go. The first row is entirely traced. And what are the general recommendations for this? So always keep the same pattern you made. So this pattern here you see for every stitch I did. This guy and in horizontal wire 45 degrees. Sorry, 45 degrees. Horizontal 45 degrees. Horizontal 45. So I'm gonna keep this this pattern on the other layers, on the other rows. So when I'm going to do when I do this second row here, I'm just gonna do this again. So then it's done. What I'm going to do on Tuesday, on Tuesday, I hope I have all the rows and columns wired already, and I'm going to do this tricky part here, where I'm going to wire the microprocessor and the capacitors and the crystal. This is a critical part, right? So wiring the microprocessor and the SMD parts is the critical part, because you have to, seldomly you'll have to move the components here and there and away and back, because since these components they are SMD, they can access only one side of the PCB, and I'll show you guys how to deal with that. Okay, so I'll start streaming again on Tuesday, 8 p.m. Brazilian time or 3 p.m. Pacific Standard Time. And the next stream we'll do this tricky part here, right? So you guys have any questions? Yeah, the chat's quite quiet, so I reckon you guys don't have questions. Well, okay then. Next Tuesday I'm gonna be back on stream to show you guys how to wire this critical part here. Thank you guys for tuning in, and always when you have questions, just hit me up on Discord. See ya.